Oh, it's awful.
I haven't seen any of them.
Alright, so there's just something called Bessel's equation, and if you ever wondered what's the function that describes the water ripples, so if you throw a rock in the water, then there's the water ripples created by this, and if you take a cross section of it, the function goes like that, right? And that function is described by this equation called Bessel's equation. Now, this is the case where x equal to 0 is singular, as I explained before, because if you divide by x squared, then x over x squared becomes 1 over x. So you can see that x equal to 0 is a singular point. And therefore, you don't have a power series solution. Rather, you have a solution in the form of Frobenius, which we say y equals to x to the r sigma n equals to 0 to infinity of an x to the n. Now, even if this differential equation does allow one solution that looks like this, it doesn't always guarantee that you have two distinct solutions that look like this, so that you can take c1 of one function plus c2 of another function to get two free variables. In most cases, what happens is that if it's a singular point, and if you try to solve for one of these cases, you will only get one solution with one free variable. So you will find out that all the coefficients an are either 0 or it depends on a0. So that's what you're going to find. And some rare cases you do have two free variables, which means you found the most general ones. But in most cases, you'll just find one of them. And the other solution may also look like this, or may not. Okay? In the case when it does look like this, then you would just find both solutions this way and find the general solution. But in our case, the other solution, there will be two types of solutions, and only one of them will be expressible as this form. And therefore, such a solution to this Bessel's equation is called Bessel function of the first kind. Usually they use J for this function. Usually people use J. By the way, this n and that n is different. Usually the solution of this form is called Jn of x. But to simplify our calculation for our purpose, let's just use n equal to 1 case. So I just want to show you how to get J1 of x. And later on, maybe if you have time, you can try to do it for other cases, n equals to 2, 3, 4, 5. Yeah, you can try them. Very similar to what we're doing. All right, so this is our first attempt at trying to solve a differential equation in the Frobenius form. And it relies on two things. One is that you're trying to figure out the solution of this form, so that's the Frobenius type solution. And another assumption when you write this is that you're going to say A0 is non-zero. What does that mean? It means that if A0 happens to be 0, then we're not going to call that as A0. The first non-zero term that you see will be called A0. Okay, well, that may have been a little cryptic, but maybe I'll have some chance to explain what I mean by that later on. Okay, but here's our assumption. Our assumption is that the solution must look like this, and we're going to assume that the very first term is not equal to 0. Okay? So let's try to solve it. Solution by Frobenius method. Okay. Let's multiply this to the inside so that you get sigma n equals to 0 to infinity an x to the n plus r. And then if you differentiate, n plus r comes down. And what would I put over here? I'm just differentiating this. How do you differentiate this? This number comes down, and what do you put here? What do you put?
N plus r minus 1.
Good. And you start from n equals to something to infinity. Now, for Frobenius method, for a power series, we always start with 1, right? But Frobenius method, you start from 0 still. Now, why is that? Well, if n is equal to 0, n plus r is not guaranteed to be 0. So you can no longer say that we can throw away the very first term. In most cases, it's not going to be 0. So n equals to 0 would be what we need. Again, differentiate. This will come down, and you have n plus r minus 1, an x to the n plus r minus 2. And now we plug everything in here. And I mentioned before that when you try to solve by these power series types, you want to multiply things out before you plug things in. So on here, I'm going to plug in what we computed here. We have y double prime is this, so we put n plus r minus 1, an x to the n plus r minus 2, plus x times sigma n from 0 to infinity n plus r, an x to the n plus r minus 1, plus x squared sigma n from 0 to infinity an x to the n plus r minus sigma n from 0 to infinity an x to the n plus r equal to 0. So that's what I got just by plugging these into this equation. All I did was I just substituted y double prime, y prime, and y in there. Okay, the solution is very similar to what we used to do for a power series solution. You go bring things inside, and this gets added to the power. If we do that, let's see what we get.
We haven't gone over yet how to find R, right? Like in the last class when we went over this at the end, we didn't really.
Right.
We didn't find, like we didn't.
Yeah. So R will end up being a special value, but we didn't go over yet how to get the value of R.
Okay.
It will appear naturally. Okay, so after bringing all the coefficient functions into the sigma, this is what we get. And what's the next step? What's the next step?
Plug and draw M.
No,
Them all the same exponents.
make them same exponent, right? N plus R, N plus R, N plus R. That's good? That's not good. So what do we do?
Minus 2. Yeah.
Yeah, we have to do the shifting on here, right? So this thing, this one only, has to be shifted. So if I replace n by n minus 2, when I have n minus 2 equal to 0, if I have n minus 2 equal to 0, that becomes n equals 2. 2. This one, n should also be replaced by n minus 2. Actually, n minus 2 plus 2 is just n. So that's what we get. Maybe I should write this. Okay, so that became this. All right. Now you can write down what happens for each n, right? Okay, so n equals to 0, what do we get? When n is equal to 0, we get r minus 1, r minus 1, a0, plus r a0, and minus a0 to the times x to the r. That's what we get for n equals to 0, right? For n equals to 1, what do you get? So n is replaced by n plus 1. No. N is replaced by 1. 1 plus r times r, a0, plus 1 plus r, a0 minus a0. X to the what power?
R plus 1.
1 plus r. So this plus this, plus, and then starting from 2 and afterwards, you see all of these sigmas starting to manufacture terms at the same time. So what do? We put a single sigma, n from 2 to infinity, and we write everything down together, right? So it's n plus r, n plus r minus 1, an, plus n plus r, an, plus an minus 2, minus an, x to the n plus r.
Would that equal 0?
Is equal to 0. All of this is equal to 0. Okay? Yes.
You meant to put A1 for n equals 1, right? Instead of A0.
Oh, thank you. Thank you. Any other questions? Okay, so now what do we do?
The reconnaissance thing.
Hmm?
The rate?
What?
Something.
The rate?
Like a double R thing.
Yeah, recurrence relation. This setting this equal to 0 gives you the recurrence relation, right? But what we are trying to use is the fact that if you have some power series and you have coefficients and it's equal to 0 for all values of x, then we know that each coefficient must equal to 0. Okay? And that's how we get the recurrence relation. So let's look at the very first thing that we have. We have r minus 1 times a0 plus r times a0 minus a0 equal to 0. That's the very first thing that we get. And then we have r squared minus r plus r minus 1, a0 equal to 0. If you factor the a0 out because that's common, and if you multiply this out, this is what you get. This becomes this, and r is from here, negative 1 is from here. And these two cancel, leaving you with r squared minus 1, a0 equal to 0. Now when can this happen? Either r squared is 1 or a0 is 0. Okay?
Oh, yeah.
Now what? This can't happen. Why? That was our assumption, okay? Our first, that's why it's always important for our Frobenius theorem to start with the assumption that a0 is not equal to 0. Because once you say a0 could be 0, then the cases branch out and it becomes very complicated. But you can always assume this and get the Frobenius method. Yeah, I didn't fully explain why we can do that, but you can do it. Okay, so you can say a0 is not equal to 0 for the Frobenius method. So this case we don't have to consider. And you get actually the two values, r equals to plus or minus 1. Now, so it looks like r has to be either 1 or negative 1. And this is a general theorem for Frobenius method. The general theorem says that if you have two numbers, then the Frobenius method always exists for the higher one. If the two numbers are apart by non-integers, if this minus that was a fraction, not an integer, in that case, the lower one will also always have a solution. Okay? However, if they differ by an integer, like this case, 1 minus negative 1 is what? 2, right? In that case, you don't have a solution in, you may not have a solution for the lower one, okay? And that case has to be handled in a completely different way. Well, it's rather than, so either, if these are integer apart, then the Frobenius theorem says either it still does have the solution of this Frobenius type, of this form, or you may have to add a log of x. So that's the general theorem. We'll come back to this later. But since I just wanted to demonstrate the Frobenius theorem by trying to solve the bessels equation, I'll just take the higher one because I know that always exists, and I don't have to worry about whether I should put the log of x or not. Okay? So I'm going to delete this. I'm only going to work with r equal to 1. Which helps us a lot, because if r is 1, then the second equation right now is what? 1 plus 1 is 2 times 1 times a1 minus 2, no, plus 2 times a1 minus a1 has to be 0, right? And that's 3a1 equal to 0, so you get a1 as equal to 0. Okay? And then after this, you'll find out that all the other coefficients will be some multiple of a0. Okay? So that it only gives you a solution with one free parameter, which tells us that you're not really getting the full general solution of this, but only half of it. Okay? All right, so let's continue chasing it. So that's what we got for the n equals to 0 and n equal to 1. Now we have to look for the recurrence relation. What's the recurrence relation? Let's copy this down again, but with r equal to 1, okay? So n plus 1, n plus 1 minus 1, so that's just n. And then an plus
n plus 1.
n plus 1 an plus an minus 2 minus an has to equal to 0. Okay. Now, I can gather the an's together. Let's see, what does that give us? This is n squared plus n plus 1 minus 1, everything with an, but an minus 2 is different, so I can't combine these two, so they're separate. So all I did was I took these three terms and factored the an's out. Now 1 and negative 1, they cancel. N plus n is 2n, so you get n squared plus 2n. An equals to negative an minus 2. I just moved that to the other side. And for Frobenius method, you're supposed to solve with respect to the higher index, right? So since n is bigger than n minus 2, I have an equals to negative 1 over n squared plus 2n, an minus 2. By the way, when is this valid? N greater or equal to what?
2.
2. So this starts from 2. That's what we have. And then let's further rewrite this as n times n plus 2, because that way we can figure out some pattern quickly. All right, so since it starts to be valid from 2, let's plug in 2 and see what happens. A2 is negative 1 over 2 times 4 times a of 0. Right? And a0 is a free parameter, so that's good enough. And I don't want to write down 8 because I want some kind of pattern to emerge. Okay? This way we'll see some pattern emerge. Now let's plug in n equals to 3. What do you get? A3 is negative 1 over 3 times 5 times A1. But what's A1?
0.
A1 is 0, so A3 must be 0. Now, you realize that if you plug in odd values, then A1 times something is A3, and A3 times something is A5, A5 times something is A7, so what does that imply?
All odds are 0.
Yeah.
All the odd ones will be 0. So in general, you'll see that A, 2n minus 1 is 0. All the odd ones will be 0. Okay? All right, now let's then move on to do the even ones. A4, that's the case when I said n is 4. That's negative 1 over 4 times 6 times A2. But since A2 is this thing, I now have negative times negative is positive. So it's positive of 1 over 2 times, actually, 4 times 6 times 2 times 4. A0. Now for A6, it'll be negative 1 over 6 times 8 times A4. But A4 is this, so I will have negative 1 over 6 times 8 times 4 times 6 times 2 times 4, A0. Now, you kind of see the pattern now, right? 6, 4, 2, 8, 6, 4. That's what's going to happen, right? So let's see if you can guess what A8 is just by looking at the pattern. It's every time you go to the next one, the sign will change, right? Negative to positive, positive to negative. So this one will be positive or negative. What do you think? A8 is
Positive.
positive. And what should I write? 8 times 10, 6 times 8, 4 times 6, 2 times 4, A0. That's what's going to happen.
Over one.
1 on top. All right, now let me try to write this again by, it's better if you write it as 2 to some power. See, this is, how many even numbers do you have? 1, 2, 3, 4, 5, 6, 7, 8. So if you have 8, you have 8. If you have 6, you have 6, right? If you have 4, you have 4. Okay? So there are 8 even numbers. So I'm going to factor the 2 out so that I get equals 1 over 2 to the 8th power. Then it's a lot easier to write because it's 4 times 5 times 3 times 4 times 2 times 3 times 1 times 2. Easier. Okay, see what I did? I just divided everything by 2. All these numbers are obtained from here just by dividing by 2. Moreover, I can see that if I just do 5, 4, 3, 2, what's that? That's 5 factorial, isn't it?
Yeah.
Right. And then 4, 3, 2, 1, that's 4 factorial. Right? So I have 1 over 2 to the 8th times 4 factorial times 5 factorial. A0. And therefore, I'm ready to write down the general form. If you have a of 2m, so let's say n is equal to 2m for some m, okay? I don't care about the odd terms because they're going to go away, okay? Then it's going to be -1 to some power, because if you just multiply -1 over and over again, it alternates in signs. And I think that's right, because if m is 1, it's negative, right? If m is 1, it's negative. So having a -1 to the m is the correct one. I mean, if you wanted to alternate, it's either -1 to the m or -1 to the m plus 1. And I choose m because that matches with this one. And then 1 over 2 to the 2m, right? Because you see an 8 here and 8 there. These two numbers must match, so these two must match. And then I see that 4 is like half of 8, right? So what factorial should I write here? So if it's 8, I need 4. If it's 10, I need 5. So if it's 2m, I need If it's 2m, I need m. And the next number is just 1 more than m, so that's m plus 1 factorial times a0. Okay? And therefore, I can now go back to our original solution. What was the solution? Y is equal to x to the 1, because r was 1. Sigma m from, I think it started with, oh yeah, m from 0 to infinity of -1 to the m, 1 over 2 to the 2m, m factorial, m plus 1 factorial, times a0, and x to the 2m. So that's what you get. You might wonder what would happen if m is 0, because this is true for m equals to 1 and after. But that's still okay, because -1 to the 0th power is 1, 2 to the 0th power is 1. Do you know what 0 factorial is? That's by definition 1, okay? And 1